Poisson equation. The classic Poisson equation is one of the most fundamental partial differential equations. Although one of the simplest equations, it is a very good model for the process of diffusion, and comes up in many applications. It is therefore fundamental to many simulation codes to be able to solve it efficiently and accurately. This example shows how to set up and solve the Poisson equation for a scalar field on a unit line. Both the diffusion coefficient, d, and source term, f, are assumed to be constant and equal to 1. Homogeneous Dirichlet boundary conditions are prescribed on all boundaries of the domain. One can derive an exact analytical solution, which is used to measure the accuracy of the computed solution. The tutorial can also be run by selecting Model Examples and Tutorials, Classic PDE, Poisson equation, from the File menu, and followed along with the step-by-step instructions in the user's guide. To start a new model, click the New Model toolbar button, or select New Model from the File menu. Select the 1D radio button. Select the Poisson equation physics mode from the Select Physics drop-down menu. Press OK to finish the physics mode selection. Geometry mode. Press the Create Line toolbar button. Enter 0 into the line geometry minimum x coordinate edit field. Enter 1 into the line geometry maximum x coordinate edit field. Press OK to finish and close the dialog box. Grid mode. Switch to grid mode by clicking on the corresponding mode toolbar button. Enter 0.01 into the grid size edit field. Press the Generate button to call the grid generation algorithm. Equation mode. Switch to equation mode by clicking on the corresponding mode toolbar button. Enter 1 into the diffusion coefficient edit field. Enter 1 into the source term edit field. Press OK to finish the equation and subdomain settings specification. Boundary mode. Switch to boundary mode by clicking on the corresponding mode toolbar button. Select 1 and 2 in the boundaries list box. Select Dirichlet boundary condition from the Poisson equation drop-down menu. Enter 0 into the Dirichlet coefficient edit field. Press OK to finish the boundary condition specification. Solve mode. Switch to solve mode by clicking on the corresponding mode toolbar button. Press the toolbar button with an equals sign to call the solver. After the problem has been solved, FEATool will automatically switch to post-processing mode and plot the computed solution. Post-processing mode. To visualize the error, plot the difference between the computed solution and the exact analytical solution. Press the Plot Options toolbar button. Enter the expression into the Surface Plot Expression edit field. Press OK to plot and visualize the selected post-processing options. Similar to this example, the Poisson equation solved for the unit circle and sphere also allow for exact analytical solutions, and can similarly be used as PDE validation test cases. The tutorial is now complete, and the model can be saved as a binary file, exported as a MATLAB M script file, or a GUI playback file.